Welcome to the next class on variational methods for computer vision. We talked about image segmentation last time, the basics, the more historical approaches to image segmentation. One of the simplest methods for segmentation is thresholding, where you basically assume that objects is dark, background is bright, or vice versa actually. The histogram tells you a lot about the brightness values, and it tells you something about how to choose an appropriate threshold. And so one of the things you can see in this example, this is the input image, this is the histogram. It basically, and here you have the brightness, and here you have essentially the frequency, how often you see colors, pixels of a certain brightness. And it tells you that there is a lot of bright pixels of this specific brightness and a couple of dark pixels that have a brightness in this range. And so you can already see that the background has a fairly uniform color. Most pixels, or the dominant number of pixels, have a specific color. You see that the objects themselves don't have a very specific color. It's a little bit distributed, but basically you see that the region of the coins is most likely these points here. And so if you select some threshold in between, you'll get some segmentation. In fact, you see, if you choose a threshold in this range, it doesn't really matter too much. The results are going to be comparable. But you see, there is a dependency on the threshold, of course. If we set 100 the threshold, the range is 255 here. If we set it to 100, we don't really get the objects perfectly. They're quite broken up. With higher thresholds, we get more and more of the objects in the segmentation. But what you see is with higher thresholds, we also get some darker background structures as part of classified as object, if you will. And so, in some sense, even in a very simple image like this one, where as a human you clearly see the objects, even for such simple images, thresholding typically doesn't work. It doesn't do the trick, it doesn't give you a perfect separation. There are some object pixels which are classified background, some background pixels which are classified object. One of the things that is missing in the thresholding approach is any notion of spatial context, any notion of spatial continuity. One of the things you can do in a segmentation approach, but that is not in the thresholding, is you can say, well, how likely is a pixel background if all its surrounding pixels are object? Just one individual background pixel, pixel classified background, although all the neighbors are saying object. And so one of the challenges is to bring in that notion of spatial context in order to find segmentations which look at both the local brightness but also at what the neighbors say. Much like in a democracy where you ask your neighbors, and if all your neighbors have a certain opinion, at least in human society, you tend to adopt that opinion to some extent at least. And so you can try to mimic such decision processes in algorithms as well, and we'll see a little bit in a while. A little more about thresholding though before we continue. As I say, there are many ways to choose the threshold. Otsu's method from the 70s is one of the oldest methods. There are other strategies, taking the average brightness, taking some spatially adaptive average brightness. You can take the average brightness in a certain vicinity and then threshold the brightness with a threshold that changes from location to location. So you can make the thresholding actually rather sophisticated. This may be useful if you have images where you have a predominantly dark object on white ground, but maybe due to lighting there's a certain intensity variation in the image. Then you don't want to select one absolute threshold for all pixels in the image, but you want to make it dependent on where you are in the image. If you are in a bright area, you will take a different threshold than if you are in a darker area. And so you can actually generate adaptive thresholding techniques that are quite sophisticated. The next thing is you can try to actually find a threshold and a segmentation by alternating. Once you compute a segmentation with some threshold. It tells you what regions are object, what regions are background, and based on that segmentation you can compute what is the typical average intensity of the object, what is the average intensity of the background, and then you take a threshold exactly in the middle. And then you resegment the image and you alternate that, and what you end up with some kind of color or brightness based clustering. And to do this systematically leads to so-called clustering algorithms. Another thing you can do, I mentioned it last time, is this double thresholding, where you say the brightness should be larger than one very large threshold, and in addition you will take pixels that are not as bright but still somewhat bright and are connected to the brighter ones, and that is also, you can imagine, a little more involved. For example, computing this kind of connectivity means it's a little bit more intense in terms of what you have to implement, what you have to program, and the runtime will go up a little bit. But the results may improve. And so you can see with these kinds of double thresholding techniques, you know, people have tweaked these strategies all the way almost to the limits. Thresholding has many advantages. Typically it's very fast. If you make it very adaptive and introduce connectivity, it may not be as fast anymore, but nowadays it's still real-time capable. And so this is one of the main reasons why it's extremely popular, because you can run it in real time, even on very cheap hardware. In addition, you have adaptive variants, which can sometimes improve the performance in real-world conditions, in conditions where the object is not perfectly dark and the background is not perfectly bright. But one should be honest, there are many drawbacks of thresholding. It's somewhat simple. I mentioned already, it neglects spatial context, so it doesn't look at what the neighbor pixels vote for, it just asks every pixel independently. And this aspect of spatial context, turns out, is extremely important for image understanding. Whether a brightness is bright or not, for example, depends on the spatial context. And humans too extensively use spatial context in very sophisticated ways. And up till today, it is very hard to reproduce the way humans use context, contextual information to interpret images. So this is an important shortcoming here, but it is to a large extent an open research challenge. There is a more systematic approach to tackle thresholding, and this leads to clustering methods, so we'll talk about that in a bit here. The idea of clustering techniques is to just consider pixels as elements in some color space, in a brightness space or in an RGB space, and then group all those pixels that have similar color, right? So you can just take all, we'll see examples in a second, but if you take your space, red, green, and blue, let's say, for a color image, and then you have some pixels in this area, some pixels with colors in that area, some pixels with colors in this area, and so what you try to find is clusters of similar color, where you say you try to find these clusters where the color is similar, and then the question is how you represent clusters, maybe by a Gaussian with the mean and some standard deviation, and then some algorithm that typically finds clusters. There are many clustering algorithms. If you are interested, I recommend actually the MATLAB help is not so bad. It tells you a lot about the number of clustering techniques. The most common one is the so-called k-means clustering. What it does is typically you have to fix the number of clusters, k, so 3 maybe in this example, and this is a user choice. And then it alternatingly, it randomly initializes the 3 clusters or the k clusters, and then it assigns all the points to the nearest cluster. And once it's done the assignment, it recomputes the mean of each cluster and, say, the standard deviation. And then you can alternate this process, and typically this converges extremely fast and gives a fairly good clustering. There are examples, of course, pathological cases where this strategy, alternating optimization, leads to suboptimal clustering. You can find examples of this, but in general it works fairly well. In addition to taking just the mean, as I said, you can consider a Gaussian distribution, and there are two degrees of sophistication. One is that you just represent the cluster with some, let me color it differently, with some mean, and then some variance sigma or standard deviation that says how large is the cluster. And the next level is a multivariate Gaussian, which means essentially that you're fitting ellipsoids, meaning that you have different principal modes here to determine, and then you can determine which distribution each sample point belongs to, and again you alternate to fit the mixture. You can do that, you can implement it yourself, but much easier is actually to go with MATLAB. It has a number of these clustering algorithms already built in. So here is some examples. This is the input, this is the result by Otsu thresholding, and this is if you do two clusters with the k-means algorithm. With k equals 2, you get almost the same result, as you can see. If you use 5 clusters, it means you partition all the pixels, you group them into 5 groups of brightness based on their brightness. This is this one. When you run the clustering algorithm, it randomly assigns a brightness to each cluster. Of course, to represent the image, as I said, you would then replace each pixel with the mean color of that cluster. And I've done that here, so you just take exactly that clustering that is in false colors here, and then you assign to each of these 5 regions the mean intensity, and you get this image. And now you see you get an image that is very similar to the original, and you've grouped all pixels into 5 regions and assigned each region one of these 5 colors. And this is the same with 10 regions. And so what you're doing here in principle is a form of segmentation, because we are partitioning all pixels into groups. But it's actually a little more what people would call color quantization. You just quantize all the color into coherent groups, and so you get a fairly good approximation of the original gray value image with just 5 colors. So this could be used for image compression, for example. Let's look a little more at segmentation in a more principled way. And these are so-called region-based segmentation methods. The thresholding was one region-based segmentation method, but we saw it was a little limited. There is no notion of spatial context. And so what we can try to do is formalize segmentation in a little more abstract way, in particular this notion of region-based segmentation. And so we say what we want to do in segmentation is we have the image plane omega, and we want to partition it into disjoint regions. Regions that we call omega 1 through omega n. So these are all subsets of omega, in a way that their union forms the full set. So we represent the whole region. That first constraint basically means each pixel of the image plane omega must be in one of the regions. Then we have another constraint that says these regions should not overlap. They should be pairwise disjoint. So if I take 2 different regions, omega I and omega j, then their intersection should be the empty set. Otherwise, I have pixels that belong to multiple regions. I don't want that. I want a hard separation into disjoint set regions. And then we have this third property for region-based segmentations, and this is this regional property. We call it P here. It's a little bit abstract. It's some property, and P of omega I equals true means if I take all pixels that form the region omega I, that property holds. This is a bit abstract. An example would be the brightness is in a certain interval, or the variance of the brightness is no more than something. But if I then take two regions, omega I and omega j, two different regions, and look at their union, that same property should be false. So meaning if I combine a region omega I with a region omega j, the joint region should no longer have a brightness variance in a certain range, in that specific range, for example. And so this is the idea of region-based segmentation. It means that each region is in some way homogeneous. The color is consistent. But two different regions have different colors. Meaning if I take their union, then the color of the overall union should not be consistent. This is the idea of region-based segmentation. And in addition, as I said, typically one would like to impose some kind of spatial context as well. Some information that neighboring pixels favor the same region. Let's look at some examples of region-based segmentation approaches. These are two methods that are very interesting because they lead to optimization techniques ultimately. But in their original formulation, they are not formalized as optimization methods. The first is called region growing. It goes back to a paper by Adams and Bischoff in '94. The second one is called region merging, and it goes back all the way to 1970. Both methods are similar, but in their principle, but they go slightly different ways. The idea is that you want to find such a segmentation by aggregating pixels into regions. So you have your image plane, you have lots of pixels, and you want to group these pixels into regions. And the question is, how can you do that? And these are iterative approaches to do it. Region growing, the name says it all. You start with a couple of seed pixels. How many is up to you. Ideally, for example, you can start with all pixels being a seed pixel. And then you iteratively grow these regions. So you iteratively include neighbor pixels as long as their color is sufficiently similar. So you look at one pixel, maybe it's black, and then you check which of the neighbors has a color that is within some threshold or some range of that black color, and you include those, and then you iterate. And you can imagine how this grows gradually, and then if you select these parameters for growth appropriately, you can get very nice segmentations. The alternative is an approach called region merging. It starts with a partitioning for which each pixel is its own, and then it merges neighboring regions. This is in the first step similar to region growing. Pixels get aggregated, but in later step you don't individually accumulate more and more pixels, but you actually fuse regions. So what you could expect is that this may be slightly faster. The advantage of these techniques is that they are interactive in some way, and they always determine connected regions. By construction, what you get is something that is connected because it grows or it fuses neighboring regions. The drawback is that there is some threshold or parameter values that you have to set. You see, in both cases, we say fuse or merge if they are sufficiently similar. And whenever you read scientific papers and someone writes sufficiently similar, you have to be cautious. You have to stop and say, wait a second, who tells me what is sufficient and what is not? So this is, in some sense, a hidden parameter in there. And you can imagine if you take a different notion of sufficient, you get a different result. And which notion is the one that is right for this image, you don't typically know. And so this is the issue. You can set parameters that work perfectly for one image, but you get the next image and it doesn't work. And in fact, this is one of the major problems in image analysis until today. that people demonstrate amazing algorithms on 3 images, and then, you know, the application people come to you and say, oh, you have this method that works well, here's all my images, can you solve it? And it turns out the same method often does not work on other images. And usually the only person who understands where it works and where it doesn't is often the author of the method himself or herself. And this is a little bit of an issue that sometimes from reading a paper, the reader has a hard time understanding when does this method work, when does it fail. And so more and more reviewers are emphasizing that the author should make a good job in showing the reader where is the breakdown point. Where, until when does the method work, and where does it no longer work. And so we are more and more requested to include failure cases to really show, look, this is where the method does not work. Another method, and this is a method that also integrates neighborhood information in an interesting way, is a somewhat classical method called the Watershed transform. This is an example taken from the book of Pierre Soy. The idea is inspired from a natural phenomenon, and this is, interestingly, is not a region-based method but an edge-based segmentation method. So it looks at brightness edges, at brightness discontinuities, and tries to then find coherent regions. The idea is as follows. We already said that in an edge-based segmentation approaches, we want boundaries on the edges. So we look at the gradient, typically of the smoothed image. So we do a Gaussian smoothing with kernel sigma. We look at its gradient norm, and let's say this is the gradient norm. Then we can say the maxima here are the locations where we want the segmentation. And so what we can do is we can model basically a downhill process for, it's very much like looking at this as a basin and dropping water on it. And you drop drops of water at any point, and then they all go down into the basin. And then you label those points that go to the same basin with one color, and those points that go to another basin with another color. It's actually a very intuitive process. And you can implement it in linear complexity, so it's not too bad. And essentially what you do is you do a gradient descent on this height profile. So the process, to recap, is that if you want to model the evolution of where a pixel goes, you say x at 0 is the original location, and then you do dx by dt, you introduce a time, is minus d dx of this thing here, nabla f sigma norm. So this is the height profile, and then we take the negative gradient of this and go in this direction. And so if we evolve this process, this models the process of the drops going down into these valleys. It's a nice idea. It works more or less. Whether the Watershed transform is a good algorithm for segmentation or not is an aspect of debate. I think it's not a good method, but I've met many people who really like it. The Watershed transform, by the way, is implemented in MATLAB, so you can just run it in MATLAB. This is segmentations generated with the Watershed transform, and you have some parameter as well that tells you essentially whether you want a very fine segmentation or a coarser segmentation. And this is essentially the water level, right? So if I add more water, then I will get larger basins, and if I add less water, let less water drop down onto this landscape, I get smaller basins and a lot more regions. And so this is then with sigma equals 10 is the parameter, and you get a lot of regions. This is again a false color representation. If I represent each color with their average brightness as before, then this is the approximation I get. So you get a lot of regions and of coherent a lot of regions based on this watershed approach. It doesn't work super well, I find. So if you look at how similar is this image to the original, is so-so. You can drastically improve it. As you saw, we do a smoothing here of the input before we compute the gradient. And what we already argued is that if you do Gaussian smoothing, you change the location of boundaries. You blur boundaries. And as you know, there is a better way. Anyone knows what's better than Gaussian smoothing? Yes? Diffusion, and in particular nonlinear diffusion. And so what we can do is we can take, for example, a Perron-Harmonic type diffusion instead of the Gaussian smoothing, and then run Watershed on top of that. And so what we get is then a segmentation of this type, and as you can see, it somewhat better represents the original. We have not so many regions, we have very large regions as well that are fairly coherent, but still the boundaries are well preserved because the nonlinear diffusion doesn't destroy them. Here's another example close-up. This is the diffused image, and this is then the segmentation. And in fact, this shows you one of the main application areas for diffusion is as a pre-processing. You want to remove the noise, but you want to preserve the signal, and for this reason, these types of nonlinear diffusion, if you look into the literature, where do people actually use nonlinear diffusion? It's mostly as a pre-processing step, as a denoising, and then they do something afterwards. Here, of course, you can do the same with k-means clustering. You can do nonlinear diffusion first. That smooths out the noise and fine-scale oscillations, preserves the discontinuities to a large extent, and then you can do color clustering based on that. And what you see, in contrast to the k-means clustering we had before, you see that we have larger connected regions. And so this is a way to use clustering and still introduce neighborhood information, because the neighborhood information comes through the diffusion process. And that is already much better, and so this shows you that neighborhood information is crucial. What we will see in the later chapters of this class is that there are more elegant solutions to combine this, and to actually not do a two-step process of first smoothing and denoising and then segmenting, but combining both. And there are in fact nonlinear diffusions which directly give you a segmentation. So to summarize this part, we've seen a number of edge-based and region-based segmentation methods. Just to recap: the Laplace zero crossings, the thresholding, clustering, region going, region merging, and watershed. We saw that the edge-based methods exploit the notion of brightness discontinuities, always in this black and white world, black object, white ground. The discontinuity tells you where the boundary is. But we saw it's very difficult to actually aggregate that edge-based information into some coherent closed curve. The watershed is one such approach, and we'll see in the next classes more principled approaches to it. Region-based methods instead exploit similarity, so they don't look at discontinuities, but they look at coherency in each region. We saw that the last methods actually do integrate some kind of neighborhood information, either through the diffusion or Gaussian smoothing or nonlinear diffusion, or in the watershed, in the region merging, region growing, that explicitly uses some neighborhood information. But the neighborhood information enters in some heuristic manner, either in this diffusion process or in this region going approach, where we have to say what is sufficiently similar. What most of the methods we discussed actually lack is a mathematically transparent optimization criterion. For example, if you do region growing, at each step you just check for every pixel, does it get integrated into a given region or not? The question is, where does this process lead to? What does it converge to? Is there anything that is being optimized in this process? Clustering actually has an optimization criterion, but what we'll talk about in the following is actually where the optimization techniques set in, is how to make this all more principled, how to devise a segmentation approach that groups pixels into regions based on minimizing some energy or optimizing some criterion. And one should say these optimization techniques started in the late 80s and 90s. And so this is going to be the next chapter. Part 2 on image segmentation, the variational methods. And so you see a little bit this falls well in line with the whole way I designed the class, that we do it from a somewhat historical point of view. This is helpful, as I said, for you to understand where we are coming from and where we're going. And so, as you saw, there are segmentation approaches. They group the image into regions, but there is a certain lack of mathematical rigor, and this is where the variational techniques and optimization techniques enter the game. As I said, we have two approaches. One is based on discontinuity detection, the edge-based methods, and one is on the region-based methods that group pixels in terms of similarity. And similarity could be similar color, could be similar local textural information, could be similarity of the local motion in a video. So this is, you can already guess, the region-based methods are in many ways more powerful, because you can, that notion of similarity generalizes very beautifully to many aspects. The approaches we discussed so far lack this optimization criterion. The fusion into connected lines, we saw the method of Perkins. There is the Kenny edge detector. It's all a little bit heuristic. And similarly, the merging of regions and the region merging, region growing, there's a question of what is being optimized in this process. Is there any quantity that is being optimized? And if so, what is that quantity? And once you define the quantity that is being optimized, you can ask, is this really the best or the fastest or the most optimal strategy to optimize that quantity? And so putting things on an optimization level actually makes everything more transparent, more explicit, and allows you to devise the most suitable algorithm, the fastest and most optimal one. We'll now talk about what happened in the late 80s, and these are very influential approaches. Two approaches I wanted to discuss. One is the snakes, and the other one is the so-called Mumford-Shah functional. The reason why I discuss these is that these may be the most influential papers on segmentation. They've been cited thousands of times, and they are complementary in that the snakes are an edge-based method and the Mumford-Shah is a region-based segmentation method. The snakes paper dates back to 1988. The idea is that you minimize an energy. And since you want to compute a segmentation, the argument of your energy is a curve in the image, C. That is the boundary that you're looking for. One of the questions that we'll look into will be, how do you represent the boundary? The energy has two components. One, typically the data term, as I said, and one the regularity term. The data term is exactly what we said. We said the boundary should lie in locations where you have large gradient, large brightness change, the edges. So what do we do for any given curve? We measure, well, for all the points along this curve, how strong is the gradient in that location. And so we just integrate. The curve is parameterized, so C is a parametric curve here. That means you have some interval, let's say 0, 1, and then a mapping that assigns to each part of the curve. Here C equals C of 0, here's maybe C of 1/2, and then here C of 1. If it's a closed curve, C of 0 would be equal to C of 1. It doesn't have to be closed, but sometimes if you want a closed curve, then you would impose that C of 0 and C of 1 is the same. So this is a parametric curve. The question is still how you represent this mapping, but you can think of it as a polygonal representation. Or if you want more sophistication, something like a spline curve. We'll see that later. But this is the curve. And then we integrate. S is the parameter of the curve. So if Fs goes from 0 to 1 here, then basically this steps through all the points of the curve. And then we just read out the gradient at these locations, square it, and then since we want to minimize the cost, we want a strong gradient, we just put a minus sign in front. So small energy means large gradient here, right? And so this is exactly what was missing in Perkin's method, some optimization criterion that actually measures the edge strengths and that tells me for any given curve, is this a good segmentation or a bad segmentation? And this is the whole idea of optimization techniques. You first set up a cost function that measures for any conceivable configuration what is the quality of that solution. And then in the space of conceivable configuration, you compute the best one. How to compute the best one, you will see, is actually tricky here. And in fact, this energy is highly not convex. You can see that because the gradient can be anything. In any location you can have a strong gradient. If you have a very noisy image, then you will have a lot of brightness changes. And all of these are minima to your curve. And if you walk through the space with your curve, then every time you hit a gradient, local minimum, right? And so in the space of curves, you have no convexity. And this is in fact one of the key downsides of the snakes. So this is the data term. Then we get some regularity term. And here the regularity term, many regularity terms have been proposed in the literature since then. But the key idea is that you want to penalize something like the lengths of the boundary. And so here what we have is we have two regularity terms weighted with alpha and beta. And essentially we penalize the first derivative and the second derivative here. Why these are good penalties? Actually, they're not. To be honest, these are not the best penalizers you can use, but I think one has to see these. Even the data term is not the best data term. Nowadays, people do not use this kind of data term. Why? I'll get into that later. But I think we have to see all of these things from a historical perspective. And in fact, this was the first, to my knowledge, first variational method to segmentation. And so this is always an important thing, that you have to first start a new idea. And then people come later and tweak the terms individually and say, well, actually there are better data terms, there are better regularizers. But to set this up in the first place is a groundbreaking contribution. So I mentioned this already, you measure the brightness strengths with the data term, so you want the cost function measures the edge strengths along any conceivable curve. And then, as I said, you compute an optimum by saying find the curve C hat that minimizes this energy. Looks simple, is difficult. But as we know, there is one simple strategy that you can always apply to any energy, and that is a gradient descent, which means you initialize the curve somehow and then you propagate the curve so as to minimize this energy. A little bit more about the regularity. This is the regularity term weighted with alpha and beta. The first term measures something that is sometimes called the elastic length of the curve, because it grows smaller for shorter curves. And the second is something called the stiffness of the curve. It basically penalizes a more wiggly curve. And so minimizing the total energy of, I called it external or internal, is what the Snakes authors called it, the data term and the regularity term. You find curves that are both short and stiff, but still pass through strong gradients of the image. And as I said, you can minimize this, and this is what was proposed by Kaas, Witkin, and Terzopoulos, is to do a gradient descent. And fortunately, this cost function is actually in what we call the canonical form of variational methods. Why? Because we have a curve that is defined on an interval 0, 1, and we have an integration along that parameter interval of something that we call the Lagrangian of that function C. And so in this case, it's a little bit different from the case I discussed on the slides, is that we not only have the first derivative of C in the cost function, but also the second derivative. And if you go back to the Gateau calculus I mentioned, the way we get the first derivative, you may remember, is by this integration by parts. And if we have a second derivative, we have to do the integration by parts twice. And as you may recall from that class, every time you do integration by parts, you get a sign change. And so you have a minus here and a plus here. And so this is the functional gradient, dl by dc minus dA dds dl by dcs, plus d squared ds squared dl by dcss. And that whole thing must be 0, as you can see. The gradient descent looks like that, and this is crucial. Not only do you get these sign changes with every higher order derivative, but once you do gradient descent, you get another minus here, because you're going in the direction of negative gradient. And so all these signs change again, so you get plus alpha and minus beta. And you can imagine, if you do that, keeping track of all the right signs is a bit tricky. And not surprisingly, the original Snakes papers has the signs all messed up. So if you look at the original work of Kaas, Witkin, Terzopoulos, these signs are not the right way. Why that is, I don't know. I thought I should write a paper about this back then when I first detected that mistake, but then later I made my own sign changes and realized, it's a common thing to make, errors in the signs, and it's probably not worth pointing it out. Interestingly, though, this sign change is propagated into many, many papers and books, so you can see the same mistake in many papers that just copy-pasted from the Snakes. So that, the take-home message here is, even if you have a seminal paper, even if you have, super smart researchers that published some amazing paper, always check the calculations yourself. Don't trust any calculation that you didn't check for yourself. These are minor issues. As I said, the cost function is not what's being used today, but I also mentioned it. This is one of the most groundbreaking papers in image analysis, nevertheless. It's received more than 15,000 citations to date, and this is something that most researchers in our community can only dream of, to ever in their life write a paper that receives that much impact. In addition, the 3 authors got an Academy Award in 2005, an Oscar, as it's said in German, a technical Oscar. Not for the Snakes, actually, but for simulating textiles, realistic simulation of textiles, so that the authors went a little more into the graphics domain. And to my knowledge, Kaas and Witkin, the first authors, went to Pixar, I believe. Terzopoulos actually is at UCLA and is still active there. Yes, the snakes are considered the first variational approach to image segmentation. As I said, they are somewhat limited for two reasons from a nowadays perspective. I mean, this is important also to keep in mind. Once you criticize papers, there are many years in between, many years that people revisited these problems, reconsidered the problems, and improved on them. And so over the many years, there is now a consensus what things could be improved or could be done better. The first and most important shortcoming is the gradient descent doesn't work well. I actually started with the snakes in my PhD. I implemented it and I was quite disappointed in that it doesn't work at all. The reason is that you have to determine the gradient maxima and then you do a local descent. And so you get lots of local minima. If you have a somewhat noisy image, then the change in brightness in gradient tells you which directions to move. But actually, if you we'll see examples later, if you have a black object on white ground, then and you initialize your curve here, in this location of the curve, there is no gradient. The gradient is 0. So locally, you don't know which direction to go. The curve doesn't know. Because at this point, I'm in a constant brightness region, so there is 0, gradient information, and so the curve doesn't actually move. And this is even worse if you add noise. So even in a black and white world, that was the ideal case for thresholding, the local minimization is not so powerful. Of course, one thing you typically do is you can pre-smooth the image to propagate the edge information into the image, yes?
But shouldn't the regularity term somehow in an area where the gradient is basically 0, drag it?
Yes, yes. So the regularity minimizes the lengths. And so if you crank up the regularity, it will shrink the curve. Unfortunately, if you crank it up too much, it will shrink it too much, and then you may actually pass the minimum here, and if the regularity dominates, it basically contracts it to nothing. The other issue is if you initialize like this, that same regularity will exactly prevent it from growing out, and so here you already see the issue that whether you get a good result depends very much on the initialization and on setting the parameters right. And you can devise very sophisticated strategies, and authors have done that. For example, you can increase the regularity, start from the outside because the object is in the image, so if you start from the boundary, that's not bad. Start with a strong regularizer, and then reduce the weight of the regularity while you're getting closer to the object. Only difficulty is, how do you know that you're getting closer to the object? You don't. Right? This is always, these adaptive strategies always somehow implicitly assumes that there is some oracle that knows at what point I should reduce the weight. The next issue is actually, once you represent curves with a in a parametric way, as a spline curve or as a polygonal curve, there are issues in numerically propagating such parametric curves. And the issue is that you cannot avoid things like self-intersections, right? So you have to imagine I represent that curve as a polygonal curve, right? So, and when I say I move the curve, it actually means that I move all these so-called control points that represent the curve. But what can happen once you move the curve is that you can get self-intersections. So you can get curves like that where the points are like this, and then all of a sudden you don't really have a segmentation in the strict sense. all of a sudden it's not clear what's which region, etc. And this is what can happen in the numerical propagation of parametric curves. And so these are two shortcomings. One is revolves around the cost function itself, the lack of convexity. And the second revolves around the representation of boundaries. And both are choices that are no longer used. Well, they are frequently used today, but I would say they're not ideally suited for the segmentation problem. Here's an example that I implemented. If you initialize here, as I said, without any smoothing, the curve doesn't move, except as you suggested, if you introduce a shrinking with the length regularization, then it contracts the curve, but then if you initialize inside, it doesn't expand. If you smooth the Gaussian smooth the input image and then use that as an initial, then use that information for the snakes, then it does converge to the object, but of course to a blurred version of the object because I just smoothed it. Maybe you could improve by using a more sophisticated nonlinear diffusion process that preserves the edges better. So there are many kind of heuristics and strategies how to improve it. But the challenge remains to get any meaningful convergence from a larger distance and yet preserve fine-scale structures is essentially not possible in this formulation. What solutions do we have? As I said, there have been heuristic strategies to improve the performance of the snakes once they were published. The first is, for example, in the case where you initialize here, to avoid too much shrinking, you can introduce an expansion term. And these terms are called balloons, based on a paper by Cohen and Cohen. Actually, they are not brothers. They just happen to have the same name. One is in Paris, one is in the US today. And what they did is they introduced a term of this type, and as you see, what this term does is it essentially just measures the area inside the curve. And weighting this by gamma, depending on whether gamma is positive or negative, you say, I favor the area to be large or to be small. So with positive gamma, you penalize the area inside the curve. Positive gamma means you contract, because the larger the area, the higher the cost. If you take negative gamma, any area inside the curve is good because it reduces the energy, and that leads to a shrinking. And so depending on how you choose gamma, you can actually create very nice effects. You can expand curves, you can contract curves. But the question is always, typically you have to know a little bit where your object is. So if you know it's inside the image and you start from outside, then some contraction in this way may help. The next strategy to improve the performance of the snakes is to do what's called a coarse to fine approach. And that is, you saw it here, the problem in the last result was that in the smoothing we lose information, edge information that is vital, but what we can do is we can smooth the image like so. Then we run the snakes until they converge, like here. Then we reduce the smoothing and again update or iterate the snakes until they converge. And so we gradually reduce the smoothing and propagate the curve. This is a heuristic strategy that is extremely powerful for many segmentation or for many optimization strategies. Not just for the snakes, but many other cases. It's a strategy which is sometimes called graduated non-convexity. Because the idea being that if you smooth the image a lot, then you get something that is essentially convex. you minimize that, and then you gradually reduce the smoothing and introduce more and more non-convexity. The way you can see it on an energetic level, if you have a cost function that is a bit nasty like so, and you are supposed to minimize it, one idea might be, well, let's smooth it a lot first until we only have one minimum, and then we go to that one minimum, and then we reduce the smoothing a little bit. So maybe in the second iteration we might have something that is a little bit like that, and so we initialize here, then we find this solution, then we reduce the smoothing again until we, in this case, would end up at the optimum. And so you can imagine this strategy of iteratively starting with a strong smoothing to get something that is as convex as possible, and then gradually reducing is not such a bad strategy. Here again, the challenge is how quickly do you reduce the smoothing. And in fact, that leads to many, many algorithms, so-called continuation methods. So this GNC approach, graduated non-convexity, is one such continuation method, because you have a parameter that tells you how do I reduce the smoothing in every iteration. How much do I reduce it? How quickly do I reduce it? And depending on how you do it, you get different solutions. And so there is some continuation parameter involved here, the degree of smoothing in every step of the algorithm. There are other techniques, the so-called simulated annealing, or there's also a variant called deterministic annealing, which have a similar continuation parameter. And so these algorithms there are a number of such algorithms that have this strategy of iteratively modifying the problem. Basically, the idea being you start with a simple problem that is easy to solve, and then that is somehow related to the original problem, and then you make it more and more difficult with every iteration, always keeping track of the last solution. And there are statistical approaches like the simulated annealing that all fall in the class of so-called continuation methods. And so this is one of them that you can read up on the book of Blake and Zisserman. The other strategy, and this is the one that's becoming extremely popular as we speak these days, is to reformulate these original variational approaches in terms of convex energies and try to solve them in an optimal way or near optimal way. And there are different strategies to find optimal solutions to the snakes or related cost functions. One strategy is to use a discrete representation that leads to so-called graph cut algorithms, and one we'll discuss a little more in this class in a continuous setting like the variational methods typically are, and this leads to what's called convex relaxation methods. Now we come to another seminal paper, one of the early variational approaches to segmentation that was published, as you can see, almost in the same time as the snakes, maybe a year later, the so-called Mumford-Shah approach. There are many variants of the Mumford-Shah paper. Maybe if we go back to where I first mentioned the two approaches I was going to discuss, the snakes, the Mumford-Shah, one interesting aspect maybe to point that out is the snakes were published in the International Journal of Computer Vision, whereas the Mumford-Shah approach was published in the Journal of Applied Mathematics. This already tells you something about the papers. They're different. They're different in the degree of mathematical sophistication. This is a somewhat, I would say, more engineering approach. It's more physics inspired from, rubber bands and things like that are locally propagated. This is a more mathematical approach. And the consequence is that both of these methods had a huge impact. This one had a bigger, the snakes had a huge impact more in the application domains. The Mumford-Shah had a bigger impact in the math literature. I suspect one reason why Mumford-Shah had a huge impact is that Mumford is a famous mathematician. He is a Fields medalist, so one of the most influential living mathematicians, I would say. He's still active. He actually came to Bonn and organized a workshop with us in 2008. And I believe he's still working on a lot of these problems. His Fields Medal he didn't get for this paper, but earlier. He got his Fields Medal in the 70s for work on theta functions that is more related to theoretical physics and string theory. But then in the 80s, including this paper, he turned to image analysis and image processing, and later turned to shape analysis. So he's worked on a diverse range of topics. And one of his most influential papers is indeed this Mumford-Shah approach. Jayant Shah is also still active in the US. So what did they propose? They proposed to compute the segmentation of an image by minimizing a cost function, and the cost function looks like this. At the first glance, it's a little more complicated. It actually contains not 2 terms, but 3 terms. One that I would call a data term, 2 regularity terms. There are different notations that you can use. I prefer this notation. The data term, as you can see, we all know that data term. It's just a quadratic data term. It just says, I want to compute an approximation U of the original image that matches the image in this least square sense. The second term we also know. We called it the Dirichlet energy at some point. It's just the gradient squared. And now you remember the problem with the gradient square was that it tends to over-smooth the edges. It tends to blur too much, and we saw there are better, if you drop the square you get better results. But here is an interesting variant, and this is what is the key in the Mumford-Shah approach, is we don't want to compute a smooth approximation of the image, but something that is called a piecewise smooth approximation. Note what we do here is we say we want to penalize the squared gradient, but only in the regions that are not the boundary C. So in addition to the approximation U, we have a boundary C in our cost function. So we have 2 arguments, U and C. And C is a boundary, or sometimes called a discontinuity set, a set of pixels where I allow discontinuities. And so whenever I'm at a pixel where I want to allow a discontinuity, I don't penalize the gradient. And in fact, in these locations, the gradient can and tends to become infinite. It will create a jump because the jump doesn't cost. If I am at a pixel that is labeled as boundary, then the jump doesn't cost. It's excluded from the region here. That in itself is not good, because otherwise in the minimization the algorithm would simply label all pixels as boundary. Right? Then I don't pay for the gradient at all. The whole omega is boundary. So we have to regularize this in some way. We have to say, okay, we want to allow discontinuities in our approximation, but not too many. And so what we add is a term weighted by a parameter nu that says we penalize the lengths of the boundary. In other words, we penalize the number of pixels where we allow discontinuities. The crucial difference to, for example, the total variation is total variation allows jumps and discontinuities, but you pay for how much jump you do. Here you also pay, but it doesn't matter how much U jumps. If you have a pixel X where U jumps, then you pay nu, and it doesn't matter whether it jumps from 0 to 1 or 0 to 2 or 0 to 3. Any jump you pay, but you pay a constant penalty. And so the algorithm has a tendency of approximating, minimizing. This leads to a piecewise smooth approximation of the original image. But you can see it's a little more involved in terms of math, in particular because you have two arguments in your cost function, not one, not the curve, but the curve and a piecewise smooth approximation u. And that makes it a little tricky. In addition, these two arguments are mathematically different entities. One is an image defined on omega to r. The other one is a curve or a set C in omega. This is actually, by the way, talking about the curve C, this is one of the aspects why the Mumford-Shah paper was quite fascinating in the applied math literature, because there is a fairly general notion of what C can be. It could be a closed boundary, it could be an open boundary, but in principle it could also be just points, right? So in principle C could be something rather pathological, points where you allow discontinuities. And whereas here in my slides I say the lengths of the boundary here, in the paper of Mumford-Shah, the regularizer on C is called the one-dimensional Hausdorff measure of that discontinuity set. So it's a little more abstract, it requires a little bit of mathematical sophistication, but I think for the sake of this class it's enough to consider C as a boundary. So I explained the data term, smoothness term, and this regularizer that minimizes the lengths of the boundary. This length of the boundary is somewhat related to the regularizer in the snakes. The lengths, this elastic length, here it's really the Euclidean lengths of the boundary. Maybe one aspect to tell you the difference, in the snakes, the regularizer we had, one of them was CS squared integrated over ds, right? That was what I call the elastic length. In the Mumford-Shah, it's slightly different. We have the length of the boundary is just the norm of CS ds. So the difference is this square. There's many aspects that distinguish the two regularizers. I guess it's not so important here, but essentially it's the same idea. You want to minimize lengths. This is called, what I just showed is called the piecewise smooth approximation. There is one limiting case that is actually even more popular in applications because it tends to work quite well and generalizes in many interesting ways, and that is the case where lambda goes to infinity. You know, one of the things I said is that parameters are usually undesirable. One elegant way to cope with that is to try to get rid of as many parameters as you can. And here, one way to get rid of this term weighted with lambda is just let lambda go to infinity. What's going to happen is the following. Here we penalize the smoothness of u. So you have to imagine the idea. Maybe I should draw a picture on this board. The idea, if I draw it in 1D, is of the Mumford-Shah. If this is your input image, you have a certain noise, then you have a discontinuity, and then you have something more. And so the idea is that there are different regions. This is maybe one region, this is another region, and then the piecewise smooth approximation, the function u, so this would be the input image that I call I here. And the function u, after minimizing the piecewise smooth approximation, of course, depending how you select lambda and nu, will look like that. It will be smooth, discontinuous, and then smooth again. Right, so that would be my approximation u after minimizing the piecewise smooth. And in fact, the boundary, you may wonder, where's the boundary? Well, in 1D, the boundary is just a point. But in a 2D example, these points are typically a connected curve, this discontinuity set. So that's the idea of the piecewise smooth approximation. If I let lambda go to infinity, I pay a lot for any non-smooth components of U. Because the gradient of U is weighted by lambda, and so if lambda goes to infinity, it essentially means you can have jumps, but wherever you don't have a jump, U has to be exactly constant. Otherwise, you pay infinite. That's the idea here, and so this term essentially vanishes and is transformed to a constraint where U in the region where I don't have boundary must be exactly constant. And so, in other words, what happens if I let lambda go to infinity? This would be U for lambda small lambda, and for a large lambda, I get a function U that is essentially like that, right? And you can see with increasing lambda, the smoothness is penalized more and more until you get U with lambda large. That is essentially constant. And you can really see that if you have a good algorithm to minimize the Mumford-Shah, actually another open challenge in many ways, you can see that transition from a smooth to a constant approximation in the separated regions. And so the segmentation leads to, with lambda infinity, leads to a piecewise constant approximation. An approximation of the input image I by a function U, which, so typically you would write it like that. I is approximated by U, and then U must be constant in the regions where I don't have boundary. One issue here, one should be honest as well, is I mentioned in the general piecewise smooth case, the boundary can be open and it can be fractured and things like that. In the piecewise constant case, it has to be a closed boundary. Otherwise, it doesn't make sense. Because in each region, I impose constancy, and so the piecewise constant case only makes sense for closed boundaries. This is interesting because I once proposed an algorithm, we'll see later, for minimizing the Mumford-Shah functional, and someone published a paper and claimed he was reproducing my algorithm, and in the piecewise constant case they had open boundaries. They had a segmentation with an open boundary, and I looked at it and I said, that's impossible. You cannot have open boundaries in a piecewise constant segmentation, because the regions each have a constant brightness, and if the curve is not closed, then there is no two regions, it's only one region. One way that is often used to rewrite the piecewise constant case is to explicitly write down the curve and these constants u1 through un. The curve partitions the image into regions omega I, omega 1 through omega n, and in each of these regions U is constrained to take on a constant value ui. So these ui, in contrast to the function u of x, are not x-dependent, they're just numbers that encode the brightness, the brightness constant for the region omega I. And then we have the lengths of the boundary. And so this is called the piecewise constant Mumford-Shah model. There are certain variants of it, and actually this is a very interesting mathematical model, and in fact the origins of this mathematical model date back to very long ago, to the beginning of the 20th century almost. In fact, for the case of two regions and a spatially discrete formulation of a grid of pixels essentially, this model is called the Ising model. Ising is a little bit misleading because he was German, so his name is Ernst Ising, and he published this together with his PhD advisor Werner Lenz in 1920 and 25. And the same model was then generalized and studied by people like Heisenberg and Potts and others. So this model is actually one of the most influential models in statistical physics, and one of the most studied cost functions. It's a model which Lenz proposed to model a phenomenon in physics called ferromagnetism, the idea that spins tend to align in a ferromagnet. and the idea that this phenomenon tends to be temperature dependent. And there are so-called phase transitions that basically determine at what temperature I have a transition from one phase to another. And so Lentz and Ising were trying to study that, and apparently the model was suggested by Werner Lentz, and then it was worked out a little more by Ising in his PhD to model this phenomenon. Let's look at that a little bit for historic reasons. I think it's interesting to see that here we have a link between image analysis and models used in modeling physical systems. So the Mumford-Shah had this continuous representation for two regions. We maybe have a label U to map it to the Ising case. In Ising's models, typically these two phases are modeled by U equals +1 in one phase and -1 in the other phase. It doesn't really matter. Some binary variable that distinguishes which phase we're in. And in the discrete representation, it essentially means we have a grid of nodes, and each node can have one of two values, +1 or spin up if you like, and spin down or -1 for the other phase. Now we saw in the Mumford-Shah, the interesting component is this length regularity. The boundary length is penalized. Let's look at what that looks like in this discrete representation. The boundary, if I draw the boundary between the two phases here as the black line, how do I measure the length of the boundary? Well, I just check for any neighboring nodes, do they have the same value of U or not? If they have a different value of U, so if I am in region 1 here and in region 2 there, then clearly there's a boundary in between. And so the length of the boundary, the number of these little edges, is simply the sum over all neighboring nodes I and j, and then I take ui minus uj over 2 squared. Why this? Well, if ui and uj are the same, both +1, then this is 0. If they're both -1, this is also 0. If one is positive, the other one is negative, then this is either +2 or -2. Divided by 2 means this is either +1 or -1. Squared means we get exactly 1 every time we have a pair of nodes that have different values of u. And so this counts the number of edges, but since we consider all pairs, then we count them twice, right? Once this node is I and this is j, and then next time this is j and this is I. And so typically this is why we divide by 2, not to count each twice. And so this is exactly the length of that discrete curve that we see on the right. And so we can say the continuous length of the boundary can be approximated by measuring the length of that discrete curve. And now if we square this out, well, ui is +1 -1, so ui squared is always 1. That's a constant actually. uj squared is also always 1. And what we are left with, if we exclude the constants, is just the product of ui and uj. And this energy that we have here in green is called the Ising energy, the Ising potential, based on this paper by Ising in 1925. And so if we add the data term, right, that would be this one here, the least squares data term, in the discrete setting is just a sum of the intensity minus ui squared. So this is the data term that mimics ferromagnets, and it's a well-accepted nowadays model for ferromagnetism. This term here, the data term, also has a physical interpretation. If you have ferromagnetic substances, you can apply an external magnetic field, and the spins will try to align with the external field, and this is exactly the external field. And this term basically says the spin at node I is going to try to align with the external field. And so interestingly, the exact Mumford-Shah energy that we have here, if we boil it down to two regions, and if we discretize it on a grid, we get this Ising model. And that is a very powerful model for segmentation, that in itself, and of course also the piecewise constant Mumford-Shah model. If you minimize it for the two region case, it turns out you can minimize on a discrete grid, you can minimize this globally. So you can actually compute the provably optimal configuration. For 3 or more regions, this is an NP-hard optimization problem, but for 2 regions, there is polynomial time solutions. I should say polynomial time solutions once you fix the values in each region. In other words, once you fix the constants, the brightness constants. This is also something in the Ising model. You assume that the spin is either +1 or -1. Here in the Mumford-Shah, we are also estimating these constants. But if you fix these constants, then the 2 region case is polynomial time solvable in the discrete setting, and it's convexifiable and globally optimizable in the continuous setting as well. This is a very recent result from 2006, actually. But the understanding that this kind of 2-region binary segmentation can be done in a provably optimal way in using graph cuts goes back to the late 80s, 89 actually. And this is the so-called graph cut algorithm. I don't think I will spend too much time in this class on the algorithm, but here's an example. So for the coin image, you remember we had a hard time thresholding even this original image to really separate the object and background. It turns out once you use a boundary regularity, like in the Ising model or the Mumford-Shah, you can even segment these types of images that are much more nasty, where you have a lot of noise, where thresholding, even if you choose a good, I think this is with Otsu's threshold, this is the partitioning that tells you what's object, what's background. It's completely fragmented because the noise is also dark and the objects have white components. If you then add the boundary length regularity, this Ising penalty that says neighboring nodes should be the same color, this is the result. You get an almost perfect segmentation. And so since actually, interestingly, this was first proposed in '89, and it took another 10 years for the community to realize. So there is a very old paper by Greik and co-workers, et al., 89, and then it took another 10 years until a paper of Boykov et al., 99, that kind of reinvented this idea of graph cuts, and that sparked a huge development in graph cut algorithms and discrete optimization methods for these types of segmentation problems. And up until today, graph cut methods are some of the most powerful methods for segmentation. And so this is not uncommon for science that the groundbreaking developments are not seen by the community. Someone publishes a paper, says, look, it works, and then he's ignored for 10 years until someone else has the same idea, and then all of a sudden the community says, wow. And then often these older papers get rediscovered and someone says, but wait a second, this has already been proposed 10 years before. That said, there are developments here. 10 years means more computation power. Also, Boykov and Kolmogorov developed more advanced graph cut algorithms that actually have better run times. And all of a sudden this became of a substantial practical value because you can not only compute this in polynomial time, but this is real-time capable. So you can easily generate segmentations of this at frame rate, no problem. But that was not possible in '89. And so this is often the case with many algorithms, that sometimes if you're too early, the world ignores you. And too early may mean that your algorithm is the right way to do it, but the computational resources of your time are not there yet. And so sometimes it's actually a good strategy to kind of develop techniques that may work with more advanced technology in the future then. This, by the way, is Ising, Ernst Ising. He died in 98 in the US. He actually emigrated, so he got his PhD with Wilhelm Lenz in Hamburg and then emigrated to the US in 47. Interestingly, after his PhD, he left physics. And he didn't actually find out that his model had such an impact in the world of physics until many years later, when he was already in the US. Someone informed him that his paper had been cited lots and lots of times and that many people were building up on it. One reason was that actually when he published his thesis around 1925, his conclusion, interestingly, was that this model that we just saw was not suitable to model ferromagnetism. So if you read his paper, you find, and therefore I conclude that this is not a good model for ferromagnetism. One reason why he did is he wanted to model phase transitions, etc. But in his PhD, he studied the model in one dimension only, one spatial dimension. And it turns out that some of these aspects of the model actually only emerge in 2 or more dimensions. And it turned out that what was not possible in a one-dimensional case actually did work in 2 dimensions. And this was something that people later showed. And that sparked the interest in this Ising model. The Ising model that, as I said, was developed in collaboration with Lenz. So this is the piecewise constant Mumford-Shah model that, as I said, in the discrete 2-region case boils down to this Ising model. In the discrete n-region case that also exists, it's called the Potts model. That was done in physics because you have systems that can have more than 2 spins and can have, say, k spins, and then you want a similar model. And this is called the Potts model. Today it is known that the optimization of the Potts model is an NP-hard problem, which means that we are not going to compute polynomial time optimal solutions anytime soon. The other nice thing about the Mumford-Shah model is it is quite powerful. It's mathematically well understood. At least the piecewise constant model has been studied, I would say, more than the piecewise smooth approximation because it's somewhat simpler. And so what I wanted to discuss in the following is some important mathematical results, and then I wanted to discuss Euler-Lagrange equations for the Mumford-Shah functional and potential implementations. But up until today, this is an open challenge. You know, every year new papers come out proposing better algorithms to minimize the Mumford-Shah. The reason implicitly is that in the n-region case, the discrete analog is NP-hard. Once you have an NP-hard problem, you can publish infinitely many algorithms for it, because there's always cases where some algorithm is going to work better than another algorithm. And we'll then also in the next chapter study a statistical interpretation of the Mumford-Shah that allows to generalize it to many, many other scenarios. I'll stop here and we'll continue next time. Thank you.